Hi, so in this lecture, we're going to talk about amines and amides. I guess I should put this as focusing on amides, but also we'll be talking about amines as well. Okay, so amides have this general structure where we put a nitrogen next to a carbonyl, and we could have two hydrogens attached to the amide. We could have one R group attached to the nitrogen of the amide, or we could have two R groups attached to the nitrogen of the amide, where those R groups can be different or the same, whatever. So when we have two hydrogens attached, that's called a primary amide. And again, if you want to call these things amides, go for it. And we have a secondary amide, where we have only one hydrogen attached to the nitrogen, and then we have a tertiary amide. And in addition to this, and this will be kind of, for the most part, the nomenclature, we could have acetamides if we wanted to. So if we put an acetyl group on the nitrogen, that would be an acetamide. And we could have formyl groups and benzoyl groups. I'll just show the formyl group. And that would make a form amide. We could have a benzoyl amide, a benzamide maybe, but I won't go into that anymore. This is sort of it for nomenclature of amides, is kind of recognizing when we have a primary, secondary, or tertiary amide. Now, similarly, we could have primary, secondary, and tertiary amines. This is going to be quite similar, where we have a nitrogen with one R group and two hydrogens. That would be primary. Secondary would be, let's make one of those R. Two groups attached to the nitrogen, and then a tertiary amine would be one where we've got three groups attached. The important thing is that none of the R groups can be carbonyls. Because if they were carbonyls, then we wouldn't have an amine. We would rather have an amide. We're trying to focus on amines here. We can also have quaternary ammonium salts. Where if we have four things attached, now with the nitrogen is positively charged, and this is called a quaternary ammonium. And it's usually countered by some X group, and so it becomes a salt. All right. Anyway, back to amides. Let's talk about the general reactivity and chemistry of amides. So to keep things short, amides are mostly unreactive. So amides are mostly unreactive. Okay. But amines, in contrast, amines are basic and nucleophilic. And because they're nucleophilic, amines are often used to make amides. And we've looked at that. We've shown that if you have some acid chloride and you react that with at least a secondary amine, primary amine also works. And also with that, we can have ammonia work. I should get to that. I should review that here. But if we treat that with base, then we can get to an amide. Now we've also shown the same reaction with anhydrides. And we've also shown it with esters. The difference with the ester conditions is we had to apply some heat for the reaction to occur, and I should add a plus secondary amine here. So all of these react with some secondary amine to give rise to the amide. Oh goodness, my tick marks are off. I have to do this, don't I? Okay. So these are reactions we've looked at for synthesizing amides. And so it's important to note, and this should not be a huge surprise given what we've talked about in the acid chloride lectures, that tertiary amines cannot form amides. And we've looked at that before. If you have some sort of leaving group attached to your carboxyl group, you could then react that with the tertiary amine. And this particular tertiary amine is triethylamine. You don't form an amide, instead you form an acyl ammonium species. 3 ethyl groups attached, plus here with an X minus. So that's an acyl ammonium. Usually is a salt of sorts, if it's stable at all. So we can't use tertiary, the point is we can't use tertiary amines to make our amides from something with a good electrophile. Okay. What I want to do now is talk about how to make these things from carboxylic acids, making amides from carboxylic acids using amine nucleophiles. Okay, now the general approach, this is one of the, first of all, let's just emphasize, this is one of the most important reactions in organic chemistry, really organic synthesis, just to put some industrial importance on here, because amides are so prevalent in medicinal compounds that making amides becomes very important. Now, the general approach is to add a reagent to activate the carboxylic acid. Now, there's a whole host of reagents. I'll show this kind of one example of these. But for example, we could have, and again, there's just numerous examples of these. One common approach would be just to convert the carboxylic acid to the acid chloride. For industrial processes, that can be a little bit cumbersome. So instead, we use carbodiimides instead. Okay, so the way carbodiimides work is you take a carboxylic acid and you react it with a really weird molecule that's got an sp hybridized carbon atom attached to 2 nitrogens. Now, this is a super important reaction. So the R groups on the R prime groups, I guess, on the carbodiimide are highly optimized. Okay, we had to be very careful about these because these we started by just using like cyclohexyl groups. I think we may even have some of that in the stock room. It turns out that that's a very prominent sensitizing agent, which means the more you handle it, the more likely you are to develop an allergic reaction to the chemical. So we try to avoid that and move into other things like there's a compound called EDCI that's one of my particularly favorite chemicals to use just because of how effective it is in its goal. But what this does is we first of all react this with a carboxylic acid through an acid-base reaction to get a carboxylate plus a protonated carbodiamide. Okay, now the carboxylate is going to add to the carbon of the carbodiamide to make an adduct. Where we neutralize the nitrogen that accepted the positive charge in the first step, and then we have this weird, awkward structure at the end. Now, this awkward structure can react with, I'm just going to have R groups everywhere. It doesn't matter. They're all the same, or they all could be different. I'm going to stop worrying about R primes and that sort of thing. Focus on the chemistry. That can react with a good nucleophile. This is sort of like a mixed anhydride, but it's easier to make, and it's oftentimes a little bit more reactive. But we're going to selectively attach the nitrogen to the carbonyl as opposed to the amino carbonyl. That is, we're going to attach the nitrogen to the carboxyl side of the molecule. That's going to form a tetrahedral intermediate. Now, the series of events that follow require a proton transfer and a neutralization of the oxygen negative charge. It's hard to know for sure what the order of events is, but the nitrogen has adducted and we have a neutral species. It seems likely to me that what we would want to do is let well, let's count this now. 1, 2, 3, 4, 5, 6. It's 6 atoms away. Okay, I'll go for it. But I'm going to go ahead and transfer the hydrogen over to the opposite side of the molecule. It's not super unrealistic for that to be an intramolecular reaction. And sorry if there's some subtle ambiguities to the subtleties of this mechanism. It's hard to know for sure what the order of events is in every case. But anyway, if we transfer that hydrogen over, what we can do at this point is oxygen come down, carbon-oxygen bond breaks to make a carbon-oxygen double bond, and that pushes electrons over to neutralize the nitrogen. A lot of work, but we ultimately get our amide out. Now, the driving force for this reaction is to make a very stable molecule known as a urea. So urea is when we have an amide on either side of a carbonyl, a nitrogen on either side of the carbonyl. Kind of, it's an interesting functional group. But this is a urea, and urea itself we'll talk about later, but I want to kind of stay focused on this. So what did we do? We made an amide from a carboxylic acid, but we kind of cheated because we converted the carboxylic acid into something that looks and behaves a lot like an acid chloride. It's got a really potent electron, a really potent leaving group because we can stabilize the electron density, not by having a really stable negative charge, but by having a neutral molecule. And not only a neutral molecule, but we make urea, which is inherently, as we'll see, a pretty stable molecule. So let's backtrack a little bit. We made a mixed anhydride, which served as our strong electrophile. We actually didn't react the amine directly with the carboxylic acid. This is a super practical way of making amides. It's a little bit safer to pull off and doesn't have as many kind of gases to deal with at the end of the reaction. But we convert the OH on the carboxylic acid to a better leaving group. Now, let's think for a second. It turns out that a carboxylic acid is more electrophilic than an amide. If you remember the chart, the order of events, the amide was only less reactive than the carboxylate ion. So maybe we should just take a carboxylic acid, excuse me. What if we just go directly from the carboxylic acid? That is, if we have this OH and we react this with a secondary amine, can we just mix these things together and get the amide directly? And the answer is yes, but the reaction has to be really hot. Or run at very high temperatures. So the reaction has to be run at very high temperatures. Okay, so what does that look like? Well, I mean, you could put like double deltas here. What we're doing here is we're trying to drive off the H2O water. So we boil away H2O. Le Chatelier's principle says, okay, if we have water on one side of the reaction and you're boiling it away, we're going to drive the reaction over to that product to try to reestablish equilibrium. Now it can't reestablish equilibrium, right? Because we're boiling the water away, but it's going to keep trying, and it's going to keep siphoning the carboxylic acid over to the amine. So we have to, that's used to boil away the H2O, and it allows the delta allows us to, the heat allows us to reverse from the ammonium carboxylate. So not only that, but we don't even have our two reactants. When we mix the carboxylic acid together with the secondary amine in an effort to form the amide, if we do this under cold conditions, we've talked about this, we're going to just simply see an acid-base reaction to form the carboxylate. The carboxylate is the least reactive of all of the carboxylic acid derivatives in terms of its reaction with a nucleophile. If you just took the carboxylate and isolated it separately, like maybe as the potassium or sodium salt, you'd have a lot of trouble making an amide from the amine. So what we do is, with heat, we can make the reaction, instead of just for the most part proceeding in the forward direction, we can have some reverse reaction occur. That's an important thing to recognize, because we can't just mix a carboxylic acid with an amine and hope that everything just sort of works out. There's a faster reaction at play than forming an amide. That is, we're going to see the proton transfer to make the ammonium carboxylate. So we have to heat everything up to overcome an inherently lower reaction barrier with a carboxylic acid reacting with a nucleophile, but also just to reverse the ammonium carboxylate formation. So what does the mechanism look like for the conversion of a carboxylic acid directly to an amide? The mechanism is going to sort of look like this. We're going to have to recognize that the ammonium carboxylate is going to be formed. As soon as you mix them, while you're walking over to the hot plate to set this reaction up, this first reaction has already occurred. So with heat, we're going to go backwards. And if we go backwards, we have some opportunity for the amine to instead go through a second reaction where the lone pair on the amine attacks the electrophilic carbon atom in an addition event. So we see addition occur. Then we're likely going to lose the hydrogen off the nitrogen. It's just a subatomic particle. Now the nitrogen is more basic, but we can have some equilibrium content where we protonate the oxygen or have some sort of hydrogen bonding interaction occur. And so that allows us to get to this species, which can push water off because H2O is a good leaving group to give us our amide. And that last step was the elimination. I really like this intermediate to be our tetrahedral intermediate, but any intermediate that has that carbonyl carbon as an sp3 hybridized carbon would be considered a tetrahedral intermediate. Okay. So that is the synthesis of amines from carboxylic acids. What I want to move into next is thinking about ureas a little bit more. But you know what? That is feeling like a new topic. So I'm just going to pause and we'll move that into a separate lecture to keep the videos of manageable length. Okay, so until then, I'll see you next time.